Okay, let's check this out. First thing that I consider when thinking about graphing things like this is I'm going to try to find all the zeros of, I guess it'd be zeros of G prime. So how many zeros did you guys see? 1 0?
Two.
I see 2.
I see two.
I see 2 of them. So I see as, and when I say a 0, I mean like a horizontal asymptote. So I see horizontal asymptote right there and another one right there. And so those horizontal asymptotes on my graph of G prime will show up as zeros. They'll show up as x-intercepts. So at -3, oops, -3 and, what is that one over there? It's like what?
Third line.
It's like,
Yeah, it's like
3.5.
about 3.5-ish, I'll give you that. So we'll say right about there, something like that. So those are my zeros. And then I'm going to make note, just like I did earlier, that there's some cusps. And so we're going to have some places where G prime just doesn't exist. But what I'm going to do for now is I'm going to deal with kind of that smooth part on the left side. And I'm going to ask myself, to the left of that 0, is G prime positive or negative? Because G is?
Decrease.
Yay. So it's going to show up down here below the x-axis. So we'll say something like this. And then, of course, once we get beyond 3 to the right just a little ways, we head over there to x equals 0, then G prime is positive because G is increasing. So, you know, something like that over to right there. And then right there is where I've got that cusp. And so I'm going to put the open circle. And we jump from something that is clearly, obviously, a positive G prime to obviously a negative G prime. Did I mess something up?
We said from -2 to 0, it's actually a straight line.
You said it was a straight line?
Yeah.
The slope looks like it's
Yeah,
just
it looks like it's a two slope of
It
2.
looks straight line-ish. So, oh, so you have a constant slope.
Yeah.
Okay, so if, I don't know, is it a straight line? I guess it is kind of a
It
straight
looks like a
line.
straight line.
It's the same points.
Yeah, okay, I can live with that. So let's go, so if that's what you're saying, then we would go, let's see here. So we go to 2, continuing on that curve, and then you're saying that it's a constant slope of about 2.
Yeah.
So you did this.
Yep.
Well, it should be horizontal, but whatever. I can live with that. It looks at 2, it looks like maybe that's where it would transition from a straight line or from a curve to a straight line. But it looks like it's pretty differentiable there. It'd be really hard to argue that that's a cusp. So G prime would be continuous. I can live with that. That works. But in any case, whether it's a straight line or a curve, and I agree with you that it's a straight line, when we go from x equals 0 to x equals 2, that clearly has a negative slope, and it transitioned to that negative slope in no space, right? And so we're going to get that jump. And it looks like that slope is -1. So I would go from 0 to 2, something like that. Definitely a horizontal right there. And then we've got our 0 coming up here again, but we do jump from that negative slope up to just like barely a positive slope, right?
Mm-hmm.
It's not real steep. You know, so maybe we go, I don't know, something like this. That's supposed to be an open circle. Still supposed to be an open circle, and goes on down through there, and we head off into the right side of the graph.
Isn't though at
Where
2,
that goes.
like when the line hits 2, the slope is 0?
Well, that's debatable, right? So that's why I put it like really low. You know, because is it 0? Is it 0.5? You know, this would be one of those things where I most certainly, if you had this, if you had it like that, kind of what you're describing, I would really have a hard time marking that wrong, because is it really horizontal there? Maybe, maybe not. It is really hard to tell.
Yeah.
The main thing that you would have, I would say the main things that I'd be looking for there is that you clearly have a jump, and you have a double open, and that you jump from a negative to a non-negative. I think those elements would have to be in place. But if you were a little bit above, it'd be hard to argue. If you were right on 0, again, hard to argue with that.
Great.
Okay. So, what do you think? Sean, have you ever done that before?
Yes.
Okay, so are you comfortable with that? Okay, fantastic. Any questions at all? All right, let's take a look at velocity and speed. This is where we get into a little bit of terminology that hopefully is familiar and you remember. Let's see if we can define these things here. There we go. So velocity versus speed. So let's get a couple of definitions in here. How would you guys define velocity? using words or formulas or something.
How fast something is going and what direction it's
Changing
going.
position.
So it's,
time,
yeah.
Speed and
So it's got like a magnitude and direction, it's a vector, and you said
Changing position over time.
change in position over time. So what is a different word for change in position, just like a single word?
Displacement.
Yeah, there it is, displacement. So you could say change in position, and of course, Lenny, that would not be wrong. I'm just going to say displacement because it's just a single word. And this is actually a word that's in the AP framework, and so so it's good to be familiar with it. But change in position is a very useful term as well. So displacement divided by the change in time is velocity. What about a formula? Using some, math stuff.
Delta x over delta t.
There we go. Assuming that x stands for position, I would totally agree with you. And then if we expanded that out a little bit further, we would say x2 minus x1 over t2 minus t1. That's a pretty useful formula. Comes up a lot. I mean, if you remember, like last year, I'm sure the AP test had some kind of an average rate of change on it, and that's that formula for average rate of change. Speed is a little bit different. I don't know, what kind of words or formulas or anything can you think of in regard to speed? I mean, we feel like speed and velocity are the same, and sometimes they are. What words? Like, how could you differentiate between speed and velocity?
Well, speed is not a vector.
It's not a vector, so it is scalar. So what does that mean that it doesn't have?
Direction.
Yeah, so it's got magnitude, but no direction. And so when we think about, some of the velocities that we've done in the past, you could have a velocity of like -3 or 2/5 or -29. And so with speed, that negative is not going to be in there, right?
Absolute value.
It's going to be the absolute value, and that's actually what goes in the blank there. The speed function could be represented by the absolute value of the velocity function, and that's definitely a useful thing to remember. Let's see here. I think that's all I want to say about that. Yeah. Okay. So let's talk about speed being increasing or decreasing, and then we'll get into kind of a crazy motion function and kind of play around with that a little bit. So do you remember this? Speed is increasing when? Speed is decreasing when? What are the conditions for that?
Acceleration and
Got to consider acceleration of velocity, right?
And the sign.
The sign of them, that's right. So speed is increasing when acceleration and velocity have the same sign. So both positive or both negative. You're not going to make me do my silly demonstration, are you?
Oh, we should do it.
Fine. Oh, I should still do it?
honestly,
Yeah.
It's really earth shaking. Let's do the speed is decreasing when. Speed is decreasing when they have opposite signs. So acceleration and velocity have opposite signs. Okay, so it's really simple. We've all experienced it. Got a backup. I like it. Do you have backup batteries for your backup calculator?
no, I have another calculator.
That's good, that's good. All right, so the position of a particle moving along the line is given by that crazy position function there. It's piecewise, and then you're asked for a couple of pretty basic questions there. S prime of 5, S double prime of 5. And then we get into the speed increasing or decreasing thing. So let's see how this goes for you. This is totally doable without a calculator, I think. Except until you get to D and E. Yeah, D and E, not so much. But do what you need to do. Let's get these questions answered, see if it all makes sense to you in the end. All right, so let's try this out. I feel like we start off with relatively easy questions and work our way towards slightly more challenging questions. So what is the position when t equals 1? Well, t equals 1 fits in with the top piece. And so because of that, we'll ignore the bottom piece and just use the top piece. So position would be S of 1. And I'm looking at that and thinking it's 1 squared plus 1. How about 2? Okay, so that started off pretty easily. The key there, though, is picking the right piece. Can you see how someone could mess up and accidentally choose the wrong piece? So you want to be careful and choose the correct piece. Okay, so S prime of 5. Now we're talking about the bottom piece. And you could have used math 8 here. I'm going to not. I'm going to find s prime of t. So s prime of t, well, of course, the pi squared and the pi are just constants, and so those are going to differentiate to be 0. That's kind of nice. And then that negative parentheses 2 pi plus 1 is just a constant multiple. So really all we're differentiating is cosine, or sine, right? So we end up with cosine. So it'll be the negative of 2 pi plus 1 times cosine of t. And then to find s prime of 5, it's just going to be s prime of 5 equals that same constant multiple times cosine of 5. And you could leave it that way, right? I mean, that's actually an exact answer. Does that come out to be a positive or a negative when you run it in the calculator? It is negative? Okay, so I'll just put just a little reminder to myself that that is less than 0, because I think we use it later on. Okay, so then s double prime of 2. We're kind of back to the easier stuff now, right? This is kind of nice. So to find s double prime of 2, we would find s prime of t first, and that would be 2t plus 1, and therefore s double prime of t would just be 2. And so the input doesn't even really matter, but we could say then that s double prime of 2 is 2. Still doing okay? Okay. And finally we get to D and E, where we're talking about speed increasing or decreasing at t equals 2. So we're talking about that top piece. So we want to compare velocity and acceleration. So s prime of 2 would be 5, which is positive, and s double prime of 2, we just found out, is 2, which is also positive. Therefore, our conclusion is speed is increasing, because they're the same sign. So we could just put, therefore, speed is increasing. Okay, and so was E the one where there was a lot of discussion? That's the one we were talking about over here, right? So let's talk about that. Let me give myself a little bit more room, I suppose. Okay, let's see how this goes. So if we're going to do speed increasing or decreasing, we already have s prime of 5, right? Now let's do this. Okay, so what was s prime of 5? Will you remind me of that?
Negative
Oh, what was that negative number?
2.0660.
So negative 2.660.
0660.
0660. So I'll go 066. Okay, so then s double prime, let's see here. Let's go back. Let me remind myself here. S prime of t was negative parentheses 2 pi plus 1 times cosine of t.
Yes.
Okay, so then s double prime, we could then just use math 8 on this. S double prime of 5. If you just use the negative parentheses 2 pi plus 1 cosine of t, and then you do math 8 on that, that should give you an accurate number. What does that end up being?
Negative 6.984.
9840. Let's put the other 0 on there. Of course, those numbers are both negative, so we get the same conclusion, right? But for a sort of different reason, right? They're both negative instead of both positive. So we can say, therefore, the speed is increasing again at t is equal to 5. Okay, so did the whole like positive, negative, sine, cosine thing, did you guys work that out okay? Okay, awesome. All right, so is that a pretty good refresher for you? Lots of stuff going on there, a couple different angles to approach that. Okay, awesome. All right, well, let's go backwards now. Let's go back to the mean value theorem, which is section 3.2. Let's see here, that would be right there. So there's a little video, a good video with a little graph and talking about all the conditions for the mean value theorem. I hope that you either remember those sorts of things or you watch the video. And so we come all the way back to 3.2 and look what's waiting for you. Another beautiful piecewise. Yay. All right. Okay, so you guys remember what the conditions are for the mean value theorem. The function we're dealing with has to be what and what? Continuous. Yeah, it can technically continuous on the closed, closed interval and differentiable on the open interval. And so we've got this function right here, and it says determine whether the MVT can be applied. So that's dealing with the conditions, right? The continuous differentiable stuff there. On that interval 0 to 2 pi, if the MVT can be applied, we're going to try to find those values of c. If it cannot be applied, we're going to explain why not. So let's check those conditions first. Is that function continuous and differentiable on the interval. And let's just be clear about this. The top piece is just a quadratic, isn't it?
Yep.
Strange with the pi in there, but it's still just a quadratic. And then the bottom piece is kind of a trig function with some stuff added on the end of it. Those two pieces by themselves are continuous and differentiable, aren't they? So where's our potential issue?
At pi.
Pi, where they either join or don't join or have a sharp point or not or whatever. That's what we've got to decide first. So let's decide whether we've got a continuous and differentiable function and either say that we don't meet the conditions or we do, and here's an answer for C. So let's check those conditions first. When we're confirming continuity and differentiability, there can be a certain format. I don't know.
The first equation. Cosine 2x doesn't go.
Yeah, I don't know. I think I would do this. Let's go with this.
Cosine 2x doesn't equal.
2 cosine 2x.
Because 2.8 is before pi,
Sorry, no,
so the
I put it
cosine
on
2x equation wouldn't apply.
Oh, yeah.
You have to use the first equation.
Oh, yeah.
Do you guys remember this notation right here for continuity?
It's frozen.
Oh, you remember that notation? How about that? There we go. So if you're ever asked about continuity, you really need to think about limits. So if we apply that pi from the left, that would be the top piece there. So you end up with pi over 2, don't you? So from the left, we get pi over 2. And then from the right, sine of 2 pi is just 0. 0 plus pi plus 2 is pi plus 2. And so that's also contained within that second piece. So I would say that we are continuous. And then differentiability-wise, we want to look at the derivative here. So f prime is equal to 2 over pi times x. And the other one would be 2 cosine of 2x. And so when we evaluate this at pi, we end up with 2 and 2, don't we? So as we approach from the left on the derivative, we get 2, and from the right we get 2. So it's differentiable as well. So the conclusion is, yes, the MVT applies. So we good with that? Okay. So now, what are we going to do with this whole MVT thing and this whole slope formula? So f of 2 pi minus f of 0, let's just do it like this. F of 2 pi, that would be the second piece. So let's see here, that would be sine of 4 pi, which is 0. You get pi plus 2? Okay, so pi plus 2 minus f of 0, that would just be 2 over 2 pi. So we end up with pi over 2 pi, so we get 1/2. Okay, so that's the average slope on this interval, 1/2. And we want to set that equal to f prime. And so we got two pieces for f prime, right? And this might be where the calculator came in, just listening to you. I feel like you were investigating a lot with the calculator, and I think that makes sense. I think you could do it without, but the answer is maybe a little more satisfying with the calculator. So what we would do is we'd say 1/2 is equal to the top derivative was 2 over pi times x. And then for the other one, we would go 1/2 is equal to 2 cosine of 2x. And yeah, you're right. I mean, both of those very solvable. So I'd say, for the top one, just pi over 4, huh? Right? So pi over 4 for that one. The other one, maybe the calculator really would be faster to find the intersection point between those two functions. How many did you come up with for that second part?
2.
You came up with 4. You came up with 2. I don't
There
know.
was 4.
In the range of 0 to 2 pi.
So you're going only 0 to 2. No, it'd only be pi to 2 pi. Right, because that bottom piece only applies from pi to 2 pi.
Yeah.
So is that where you got the 2 instead of the 4?
Yeah, there's only 2 solutions there.
Okay. Well, let's hear what they are really quick, Lenny.
3.8007
Okay.
and 5.6241.
5.6241. You guys agree with those two? You just had a couple of extras because your domain was too big? Fair enough. Okay, so a little more of an involved MVT, for sure, but I'm trying to like bring in as much review as I can, trying to make things as like multi-concept as I can, just so that we're having to think about a lot more than just the one little concept on the page. Okay, so what do you think? Is that okay? Great discussion. I love listening to you guys have like little math squabbles and get things kind of figured out, and that's great. That's exactly what we want to have happen. So definitely appreciate you guys doing that. All right, so we got a couple more to go here to finish up our little MVT chapter. So let's take a look. We've got example number 2. Example number 2 is right off of an old AP test. I think it's like from 2008 or 2009 or something. This one's a little more straightforward. It says the wind chill in degrees Fahrenheit, human feels based on the air temperature. And of course combined with the wind velocity v, if the air temperature is 32 degrees Fahrenheit, then the formula for wind chill is that W of v formula there. It's valid for the interval 5 to 60. So it says find the average rate of change of W over that interval, and then we want to find the value of v at which the instantaneous rate of change of W is equal to that average rate of change that you hopefully just calculated. So take a moment, think that one over. Real quick. I want to make sure that you understand like what we need to do in order to do the thing that I think you're all doing. Are you all using the MVT? Did you recognize the language of where does the instantaneous rate equal the average rate? So something that was new last year that I know as a reader, I noticed that a lot of folks just did not do a great job of. Before you use things like the IVT or the MVT, you need to confirm and mention that the conditions for that have been met. Okay? Now you don't have to go into great detail and like prove it for every single point because you'd never be able to do that. It just needs to be done in kind of a general fashion. So you look at this function here, this 55.6 function for W of v, and we need to at least acknowledge or deny that it's continuous and differentiable. So maybe you'd have a calculator. This one I know you had the calculator available to you. You could graph it and look at it and be like, hey, yeah, look, that's continuous, and it is differentiable too, isn't it? So you want to mention that. You actually want to write that down and say W is continuous and differentiable on the interval 5 to 60. Therefore, the MVT applies. Therefore, we can use it. So, once you write that down, then, of course, yeah, feel free to use the MVT. But if you are about to use the MVT, make sure that you've mentioned that the conditions for it have been met.
Yep. Is that 011?
Is that miles per hour squared?
Okay.
Miles per hour
Squared, okay.
So we're basically looking at W of 60 minus W of 5 over
Oh, wait, no, it's just miles per hour.
60 minus 5.
No, because this is the v value, so it's the x value, so mph.
And we want to set that equal to W prime. Can you guys fill me in on what is 0.16 times 22.1
0.16.
when you differentiate the W?
No, do like f of x.
0.16 times 22.1.
Yeah.
3.536.
Negative 3.536 v to the negative 0.84. What did you guys get for that difference quotient on the left, the W of 60 minus W of 5 over?
Negative 0.254.
So negative, you said 0.254 or 2.5?
0.254.
So 0.254 equals that negative 3.536 v to the negative 0.84. And this was a calculator active, and I think you see why here. Finding this intersection point is going to be problematic without. So what did you come up with for a v value there?
23.0107.
So we'll go with 011. What would the units be for that? You guys agree with that
Is it
number? I'm
miles
pretty
per
sure it's
hour?
right. Miles per hour, yeah. Yeah, so when v equals 23.011 miles per hour, that's when we have reached that average rate of change. Okay, I'd like to do one more really quick. I'd like to finish this. We got just a short amount of time. Let's take a look. It's just a multiple choice. And this would be a meeting the conditions question. It says the mean value theorem does not apply to that function on that interval for which of the following reasons? f of 0 is not defined, f of x is not continuous, f prime of 1 does not exist, f of x is not defined for negative numbers, f prime of 0 does not exist. I think a graph would be a pretty decent resource to figure this out. What do you think? Why does the MVT not apply here?
E.
The answer is E. You are correct. So f of 0 is definitely defined. You can do the cube root of 0 and then square it. F of x, you can see from the graph pretty clearly, it is, it is continuous.
Yeah.
But you get a nice little sharp point right there at x equals 0, so it's not differentiable there. Therefore, the MVT does not apply. So you might see things like that from time to time. It doesn't take a whole lot of arithmetic, in contrast to some of the other things you've done today. It doesn't take much arithmetic, it just takes a good conceptual knowledge of what's going on. So, have a wonderful day. There is a 3.4 video from Monday. Again, just kind of feel free to